All right, so first thing we're going to do today is we're going to review the law of conservation of energy, which you went over at the last class. Energy cannot be created or destroyed. It can only be changed from one form into another. So a good example of this is a pendulum. If you've ever seen a pendulum swing back and forth, the highest point in the swing, you're going to have your highest potential energy. And you're not going to have any kinetic energy for either this side or this side. There is no kinetic energy, but it will have its maximum potential energy at both of these places, which it tells you right here. So down here, however, because when the pendulum swings, it increases its kinetic energy. So your kinetic energy increases until you get to your maximum speed that is actually going. That would be your maximum kinetic energy. So straight down from the bottom is your maximum kinetic energy. Then kinetic energy again starts to decrease until you get your no more kinetic energy and your maximum potential energy. Another great example of this, and a little easier to understand, is actual swing. I know some of you have probably swung on a swing set when you were younger, or maybe you still do. So we're going to look at a swing. So on this, your highest point at A is going to be your potential energy, because at this point you are paused in the air and you are not moving. Everybody knows that moment when they pull back up on the swing, looking down before they actually start moving forward again. That is when you have your highest potential energy and no kinetic energy, because you are not moving. Kinetic energy is the energy of motion. So once you start swinging, your kinetic energy increases until you get your maximum kinetic energy, which is at the bottom of the swing, because that is the fastest it's going to go until it starts to go back up again and the kinetic energy decreases. And at C over here, you now have no kinetic energy again, and you have your highest potential energy. Okay, so when the swing is between, we're looking at this little box up here. When the swing is at its highest point A, it only has potential energy, which I explained, no kinetic energy. When the swing is midway between A and B, some gravitational potential energy is converted into kinetic energy. I'm just going to put KE here because kinetic won't fit. When the swing is at point B, all the gravitational energy has been converted into kinetic energy. Okay? So I hope that makes a little more sense when it comes to potential energy being converted into kinetic energy and vice versa. All right, so this is a short question. As the pendulum swings downward, what is occurring between points 1 and 3? So here's 1 and here's 3. I'm going to give you a second to read through the choices and see if you can figure it out. So between these 2 points, not at this point and not at this point, between the 2 points. So if you thought potential energy is converted into kinetic energy, you are correct. It can't be A because potential energy is at its highest here and here, right? Can't be kinetic energy because kinetic energy is at its highest down here. And kinetic energy is being converted into potential energy over here. Okay, so B would be the answer to this question. All right, so we're going to talk about thermal energy and heat, which basically are the same thing. Thermal means heat. So thermal energy and heat are what we're going to talk about. Then we're going to learn to calculate specific heat. So when you look at this glass, these 2 cups, one has water in it that's 30 degrees Celsius and one has 90 degrees Celsius. What will happen to the temperature in the beakers over time? If they're just left sitting, what do you think will happen? Heat, okay, when we think about these, what's going to eventually happen is the temperature in this one is going to come down to room temperature, and this one is going to increase to room temperature. So both will actually, but if these are actually connected, then they're going to find equilibrium. They're going to both get to a temperature that's between the two of them. Because basically heat is the energy that flows from higher temperatures to lower temperatures. So this one is going to decrease its temperature, and this one is going to increase its temperature. Okay? All right, so temperature is a measure of the average kinetic energy of a particle in a sample of matter. So as you increase the temperature, you get greater kinetic energy. We've talked about this when we talked about the states of matter. When you go from a solid, which is ice, to a liquid, which is water, you increase the molecules' movement, so you have greater kinetic energy with those molecules. If you decrease the temperature, you lower the movement. So if you go from a liquid to a solid, the movement of the molecules is going to decrease, therefore lowering kinetic energy. This also applies here. So absolute zero was a vocabulary word we went over weeks ago, but it's basically 0 Kelvin, okay? So basically all the particles have stopped moving. They don't move anymore. That's what absolute zero is. All right, so thermal energy is the total energy of the particles in a material. So both the kinetic energy and the potential energy. It's heat, basically. So thermal energy depends on mass, temperature, and the phase of matter, solid, liquid, or gas. So thermal expansion and contraction. Thermal expansion is when something gets hot and it expands. So for example, this balloon right here, you put it under, you heat it up, it's going to get bigger. It's going to expand. If you actually make it cold, like this one, then it's going to contract and get smaller. Hot temperatures cause materials to expand. Cold temperatures cause materials to contract. So that's basically thermal expansion and contraction. So if we take a look at these two cups, you have a coffee cup. Oh, actually, these are both tea. You have a tea, actual mug of tea, a coffee cup down here, and you have a glass of tea over here. And we're going to pretend like there's not ice in this one over here, okay? If we compare them, we say they have the same temperature. The average kinetic energy of the particles are the same in both containers, okay? They're both liquids. The temperature is the same, so the kinetic energy is the same. However, there is more thermal energy in the glass of tea because it has more particles. It has more mass. So, unlike temperature, thermal energy depends on mass. Thermal energy, also called heat. These two words are used interchangeably, so you don't get confused. You can't see that very well. All right, so now we're going to talk about specific heat, and this is going to be a calculation, but we're going to explain it first. Specific heat is the amount of energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. Specific heat is measured in joules per gram per degree Celsius. So this is how you're going to see it a lot, and this should be a little mark instead of a whole zero, but so it's a joules per gram degrees Celsius. So that is the unit for specific heat. Specific heat is going to be notated by a C, okay? Because we've already used H and S and all of these others, so C. The reason it's signified by a C is because it's a constant. Every single material has a specific heat. Water has its own specific heat. Certain metals have their own specific heat. So they actually call it C because it's a constant. It does not change. No matter what else changes in the problem, the specific heat does not change. Okay? It's actually a table in a book with all these specific heats of all the different materials. So the question here is the information you need to understand here is that the lower a material's specific heat, the lower it is, the more its temperature rises when a given amount of energy is absorbed by a given mass. And I'm going to explain this a little better with a chart. Okay, so I have a chart here. This shows that water has a specific heat of 4.18. However, iron has a specific heat of 0.449. So we know that iron absorbs a lot of heat very easily. It's a metal, it's conductive, so it does absorb a lot of heat. So this shows you that iron takes a lot less heat, a lot less energy to get it hot, basically. Okay, so this lower, because this is lower than this, means it heats up a lot faster. Okay, hope that makes it a little more clear. All right, so it takes 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so that is a constant, 4.18. How much energy is needed to heat 2 grams of water at the same temperature? So we're going to look at how to calculate this. Specific heat does not change, okay? However, the heat itself with an equation can change. So we are going to look at how to calculate this. But first we're going to watch a video.
Hey, it's Professor Dave. Let's talk about calorimetry. He knows a lot about the science stuff. Professor Dave explains. Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water, and the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension.
Okay, so why does a piece of steel heat up more than an equal mass of wood when both absorb the same amount of energy? What do you think? Based on what you just learned about specific heat, why does a piece of steel heat up more than an equal mass of wood when both absorb the same amount of energy? Well, it has everything to do with its specific heat. The metal has a lower specific heat than the wood. Therefore, its temperature increases more as thermal energy is absorbed. Okay, it heats up faster. All right, so we're going to calculate specific heat. Specific heat is recognized by this equation right here, and I'm going to break it down for you. So our heat is this Q. That is our heat. Our M is our mass, which is usually in grams. We already know this. Our C is our specific heat. And as I told you, this is a constant. And then this is your change in temperature. Sometimes you'll be given a beginning and an ending temperature. You subtract it to find the change in temperature. Okay, so we're going to use this equation to solve some other equations. We are going to have to manipulate some of these equations, but it's simple division and multiplication, so it shouldn't be too difficult, but I will show you how to manipulate the equation to find mass, to find specific heat, and to find temperature if you need to, so that you can use them when you do the assignment later. All right, so our first problem says, an 500-gram iron pot has a specific heat of 0.449 joules per grams degrees Celsius. How much heat must be absorbed to raise the pot temperature by 95 degrees Celsius? So we have our equation up here. Remember, we're looking for how much heat, so that's our Q. Okay, our Q is our heat. So Q is what we're looking for. Now let's list the rest. We need our mass, we need our constant of specific heat, and we need our change in temperature. Okay, so if you look at the equation again, mass is usually in grams. So this is our mass, 500 grams. Our constant is this here, says our specific heat is, so our specific heat is 0.449 joules per grams degrees Celsius. And our change in temperature, which it says it raised it temperature by 95 degrees Celsius, so you don't have two numbers, so you just put in that particular number they give you. Okay, so here is what we're going to do. We need to put it into the equation. So Q equals 500 grams times our 0.449 joules per grams degrees Celsius times our 95 degrees Celsius. So we're just going to multiply these numbers together. I'll give you a minute so you can calculate if you want to. Okay, so once you do that, you should get in joules, Q equals 21,375 joules. Remember, heat energy, any type of energy is in joules, okay? So heat is definitely a type of energy. So this is your answer for number 1. All right, so we're going to do a different type of problem and figure out what we need to solve using the same equation, okay? So first we're going to list what we have. It says an aquarium heater transfers 1,200,000 joules of heat. All right, so this is our heat right here. So that's our Q. So Q equals 1,200,000 joules, okay? To 75,000 grams of water. So our grams is going to be our mass. Okay? And then what is the increase in the water's temperature? Now, we actually had the specific heat for water already. It didn't put it in this equation, but it is 4.18. It was in that chart we looked at earlier. Okay, so specific heat of water is a known factor. So I'm going to write it here. Okay, so we're going to do C. And you should always be given that information when you're doing a problem. So there's our specific heat. What are we looking for? We're looking for what is the increase in the water's temperature. So we're looking for the change in temperature. Okay, so first thing we're going to have to do is manipulate this equation so that we're solving for the change in temperature. So Q equals M times C times change in temperature. Now, we need this by itself. So how would we get this by itself? Okay, the first thing we need is get everything else away from this side, right? So if you have these two multiplying to this, how would you get these on the other side? You would do the inverse operations, which is divide, correct? So divided by M times C. Okay, so change in T is Q divided by M times C. So if you want to write down this equation, you will be using it in the problems later to solve for temperature. Or you can remember how to move the equation around. It is up to you. But when it asks for the formula that I want you to use, you're going to put this one when you're solving for temperature. So let's now plug in the information. Change in temperature equals Q, which is 1,200,000 joules, divided by 75,000 grams times our specific heat of 4.18. And I can't put the units on there because I'm running out of space. So once you figure this out, what is our answer? Once you multiply these first, okay, always multiply the bottom first, then divide it into the top number. So you should get 3.8 degrees Celsius. That is your change in temperature. All right, so we're going to calculate mass now. So what is the mass of the water? Okay, so we have mass equals question mark. The other information we need is Q, which is the heat. We need the constant of water, which we ought to know from the previous question, is 4.18 joules per grams degrees Celsius. And we know that we also need temperature or change in temperature. Okay, so let's figure these out. It says, what mass of water will change temperature by 3 degrees Celsius? So that's temperature. So that's our 3 degrees Celsius. When 525 joules of heat, there's our heat, is added to it. So this is 525 joules. Now, the first thing we have to do is move this equation around. We have Q equals M, C, change in T. All these are multiplied. So we need to get this by itself. So we're going to divide it by the rest, C times change in T, right? Right, so these cancel, and M equals Q divided by C times change in T. Pretty simple to move around when it's just multiplication. There's no adding or subtracting. All right, now we put the words in, the numbers in. Q is 525 joules. C is 4.18. And temperature is 3 degrees Celsius. Make sure you do this multiplication at the bottom first. Then divide it into the top. And you should get 42. And this is mass. Mass is always in grams. So there is your answer. All right, so we're going to do one more problem, figuring out specific heat. This is a great problem if you were actually trying to find what an item was. But this, they're going to give it to you. They're going to tell you it's silver. But if you didn't know it was silver, you could use this to find the specific heat to be able to identify what type of material it is. So we have a problem here. It wants us to find what is the specific heat. So we're looking for C. Okay, we need Q, M, and change in T. So let's find those in the question. So you says if 2,575 joules of heat, there's your of heat, so that's your heat. 2,575 joules is added to a 25-gram piece of silver. Okay, so 25 grams. Grams is mass. The change in temperature of the silver was 436 degrees Celsius. So that is our temperature. It says change in temperature of the silver will be this, okay? So now we have to find specific heat. So we know our equation looks like this. We need to manipulate it so that we're finding C. Okay, so we're just going to divide this side by this and this side by this. These cancel. C equals Q divided by M, change in T, multiplied by each other. So we're going to put our numbers in. Your Q is 2,575 joules. Your mass is 25 grams times your temperature, which is 436 degrees Celsius. Okay. So once you put this all in, you should be able to find the specific heat of silver and actually confirm it on the table in a certain book, but you don't have to do that part this time. All right, so when you multiply these two numbers and divide it into here, you should get 0.236 joules per grams degrees Celsius. All right, so there is your specific heat. So you have 5 problems to work for me. I've given you all of the actual equations that you should put on or manipulate the one you have. This is not real difficult to manipulate. And if you have any problems, let me know.